I will go very quickly some of the questions that you didn't do that well on average. I'll just, unfortunately, although the same question was there, I even explained and not happy. I thought the average should be higher than what it is. Yeah, but everything was there right before. That's why that's why you need some practice. This is. All right. Okay. I'm here to not to listen to you. Well, if you have a question, ask me. Then please. All right. I see. For example, this one. Average acceleration. This is not the first time the question you saw. It has been there in the past midterm. I repeatedly told you average acceleration is not the sum of the velocity divided by 2. It is only true for constant acceleration. Here it is not moving in a straight line. It is changing direction. So you have to use average acceleration is v2 minus v1 divided by the time. So whatever the direction of v2 minus v1 will be the direction of the average acceleration. Okay, so that's the problem. A lot of them get the wrong answer because they just sum the v1 and v2. No, you have to sum the v2 and minus v1. Yeah, change the direction of the v1, then you add them, then you get the direction of v2 minus v1. That is one of it. The other one, which I made as bonus question, this one. So come on, I even kind of told you when there was the question for the M2, then I told you, you can have the for M1. I kind of indicated it, you might get that. So no, the blue one, it's M1. Yeah, for the M2, you don't have the answer, do you? Or you have this one? No, but it's M1G. It's not M2G. This is M1G. So you should. So some people ask, what is the meaning of bonus question? Let me explain because there are some confusion. Bonus, excuse me, you have 22 questions, right? But I gave the marks out of 20. That's the meaning of bonus question. That means some people may be able to get more than 100%, but I not give you more than 100%. 3-4 people got 20, more than 20. So, but their score will be reduced to only those 4 people. I mean, they don't need any extra marks anyway. Hopefully they will get full marks in all the other courses. Okay, all the other exams. Yeah. This one? Okay, direction. This one. Okay, let me show you quickly. The V1 is this, right? And V2 is this. So you need V2 minus V1, which is V2 plus minus V1. So this is V2. Okay, this is plus V1, so minus V1 will be this. Therefore, V2 plus minus V1 will be this. Okay, I mean, we've been telling you this, it's not the first time, Okay. Right, I think now I will start our lecture. So we move to the next chapter, which is the continuation of the chapter 3, because in chapter 3 we introduced the forces, and then we even looked at equilibrium. That is, we know acceleration, we know velocity. Velocity is constant, either at rest or some velocity. We call it equilibrium. Now we will continue to see what happens if when the velocity changes. So that's where the Newton's laws come in. So the content, we'll introduce the Newton's law. Then we'll revisit the free body diagram. Then we'll take the Newton's laws one by one. First law, the second law, and the third law. Please, quiet, please. And application of Newton's laws. Excuse me, you have any question, raise your hand. Please do not talk to each other. And there is what is called the apparent weight, different from the weight. We'll discuss that in that section. And we will bring in circular motion again, and with the dynamics of circular motion, that means the forces acting, because whenever there is acceleration, there should be a force to make it go in a circle. So we'll that up. Finally, this dimmed section on physiological application of Newton's laws. Okay. Yeah. Yeah, all of it. Yeah. It's three laws. I mean, they're all connected. You cannot skip one and do only the other. Right. Then, net force, that's an idea you already exposed to when in the chapter 3. What do you mean by net force? Add all the forces, right? An object can have more than one force acting on it, okay? So in that case, we need to find the total force acting on that object. So that is what net force means. But you can put it like this, or as the mathematical notation sigma, right? Summation of all the forces. This what means is F1 plus F2. Excuse me. Quiet, please. So we add all these forces and sum them up, that is net force. Remember, it is not normal summation, vector summation. You all know how to add vectors. Okay. What happened when the net force is 0? Velocity does not change. That's actually the Newton's first law. We'll come to that. Okay, we'll not. When the net force is 0, velocity remain constant. It could be 0 velocity, in which case the object will stay at rest. It may be, say, 10 meters per second. It will continue with that velocity. That's what the Newton's first law is. When you say velocity is constant, that means acceleration is 0. You can put it that way as well. So the net force, in order to say put the equilibrium condition, if there are forces in a plane, both in the XY direction, then we need to able to get the net force only in the X direction. So we can solve the question along the X-axis, or we get the net force only in the Y direction. So we can do apply the equation only in the Y direction. So in XY plane, the force vectors can be decomposed, resolved. We use the word, I don't know why it is decomposed. Okay, resolved. So I think it's better than decompose. Decompose means something else, right? Into two orthogonal components, one parallel to the X-axis and other parallel to the Y-axis. So we are revisiting free body diagram. This is an important concept. You cannot ignore the free body diagram, because when you want to find the net force, if you forget one of the forces, you're going to get all your calculation wrong, because net force means sum of all the forces. So drawing the free body diagram will force you to stop and think and make sure I have considered all the forces acting on the object. The free body diagram is a drawing that consists of all forces acting on the system of interest. And then we also look at other velocity and acceleration that are actually not part of the free body diagram. Free body diagram means the forces. Velocity and accelerations are not forces, right? They are not included. You also put the coordinate system, the XY direction, and you label any angles, say, for example, if it is an incline, you have to label the angle. It's not part of the free body. Free body strictly mean labeling the forces, showing all the forces. So let's do an example question. Draw the free body diagram for a heavy box at rest on a rough inclined surface. So it is already drawn in the next slide. So let's take, this is the incline, and here you have a box resting on the surface. So we are asked to draw the free body diagram. So the way we do that is to see what its interaction, what it is interacting with. It has a mass. If it has a mass, it cannot escape the pull of the earth. So it is interacting with the earth. So we have the gravitational force. You know, sometimes you put it like this, Fg, F sub g, or you can say the weight, or you know, it is equal to mass into g. You know, different ways of labeling it. So call okay. Then it is touching in contact with the incline. Excuse me, please, upstairs. Now your fellow students have come to my office and complained that I cannot concentrate in the balcony. So it is my fault if I cannot keep the class in order. Now, you should be concerned about the others. If you don't want to listen to me, that's fine, you know, but you keep quiet, don't disturb the others. So it is touching the incline. So you will have the parallel and the perpendicular force. Perpendicular force is the normal force. The parallel force is the friction force that is coming between the contact between the box and the incline. Now, if it is to move, which direction will it move? Down. So the friction force will be opposite direction. Okay, so that's it, right? Do we have any other? We are drawing the free body diagram for the box, right? Nothing else. Yeah, friction always opposes the motion, but it's a bit tricky, you know. Okay, when you're driving the car, what direction is the friction? The friction is between the wheel and the floor, right? Which direction is the wheel moving when the car is moving forward? No. When the wheel is touching the road, the wheel is pushing the road backward. So the car moves forward. The friction is actually forward. Because the wheel is the one that's touching the road, right? Imagine, you imagine the tire. The tire is actually pushing the flow backward. So the friction is forward. So you have to be careful, okay? It's the attempt to the motion, the contact surface, then it will be in the opposite direction. Friction is always in the opposite direction to the motion or the attempt to motion. Here it is not actually moving, but you know, it's trying to move down. That is because of the gravitational force is pulling it down. So the friction force will be in the opposite direction. So we took care of everything. Now we are doing something else here. What is it? We are resolving one of the force, the gravitational force, because our x and y is this, right? We decided to take the x like this. We can choose this way, it doesn't matter, as long as it's parallel to the incline. Now, n is in the y-axis. Good. F friction is in the x-axis. Good. But this guy, the gravitational force, is in between. So this is not good for us. It's not good. I mean, you know, we can't help it. So what we do, we break it into, resolve this into one along the x-axis and the components or resolve it along the x-axis and the y-axis. What is the reason for doing this? To make it easy for us. Because when you apply the net force in the x direction, I don't have to worry about this and I don't have to worry about this. Just these two. It's very easy to get it, right? So the net force in the x direction is F minus Wx. So we have done it already. All the forces are either in the x direction or the y direction. We can quickly write the equation. So that is the idea. So let's do an example problem. Another one. Draw the free body diagram. So the short form for this, FBD. So you should understand when I write FBD, I mean free body diagram. For a system of two blocks connected by light cord, a string or a rope. So it is there in the picture, I'll show you. So he's talking about this. Now we are making a little bit two body. Before you're only looking at one object, now we have two objects connected by a string like this. One of the boxes are moving horizontally on the table. The other object is moving vertically, hanging by the thread or the rope or the cord. Now we are asked to draw the free body diagram for this system. System consists of the boxes, the table, and the earth. So we have to study what is moving these two guys, right? And then we will draw the free body diagram for M1 separately and for the M2 separately. We cannot do all at once, so we have to take one at a time. So the box M1 is contact with the table, contact with the table. So there will be surface forces, and let me call it N1, because if there is another surface force, we can, in case. And gravitational force is M1G. Okay, so put the subscript. What else it is interacting with other than the table? Yeah, I mean, who is it? Yeah. Yeah, I forgot the friction, right? Okay, yeah, the box is interacting with the table and the earth, but I only remembered the perpendicular component of the contact force. I forgot both of these forces are from the table. Okay, sorry. Now, yeah, my question was, what else it is interacting other than the table and the earth? Tension, yeah, tension. So this guy rope is connected, so it is interacting with that process. So now we are complete. The free body diagram is complete. Okay. Now M2. Let me take the blue. The tension is in this rope, right? And on this object, the tension will be this way, and on this, it will be that way. The tension is always trying to pull the object away from the object. So are we correct in assuming this tension is the same magnitude? I mean, it is one piece of rope, right? So everywhere should be the same tension, but it's not strictly correct because I am moving it. It is touching this pulley. So because of if the pulley has friction, we cannot, it's not necessarily the same, but then the question becomes complicated. We have to know the rotational motion of the pulley. Then we didn't go there. We don't go there, okay? It has become complicated. We had to bring in the rotational motion. So we make the assumption the pulley is light, not heavy, no mass, massless and frictionless. If that is the case, it is the same tension everywhere. I mean, magnitude I'm talking about, but the direction of the tension on block M1 will be to the right. The direction of T on M2 will be up. Okay. What else it is interacting with? Gravity. Is it touching anything? No contact forces. So that's it. We are done. Finish. So we got the free body diagram. Let's move to the next. Oh, he's doing the same thing. Okay. Now, what is next? To put here X and Y direction. This is for M1, the free body diagram. This is for M2. This is the X and Y for M2. The X and Y will be separately. You have to, sometimes it happens to be the same X and Y both, but it not necessarily. Yeah.
Can do both in the same diagram, right?
Yeah. Like what you've done here. You can do it, no problem, because this is, we are learning. So we are just making it obvious. Okay, so you can do it in this itself. Okay, strictly speaking, you have to put a dot for this, and it's okay. You can just imagine this is the dot, and okay. You can be efficient once you know what you're doing. It's fine. But this is for explaining purpose. So another point I want to make. Okay, now say suppose it is like this. This is M2 and this is M1. Not hanging. So for this, your X and Y will be like this. And for this, your X and Y will be like this. And in this case, it happens to be same way, the XY coordinate system, but it's not necessarily, right? Depending on the situation, the XY coordinate system for the second guy can be different. Right. So it's kind of introducing the Newton's law. Now we come properly into the laws one by one. So we need to know about net force and so on. Now, what is Newton's first law? Probably you remember it, I hope. If an object is at rest, it wants to stay at rest. Or if it has some velocity, it wants to continue keeping that velocity, unless a non-zero net force act on it. Okay, the moment a force applied, non-zero force, net force, then it will change its velocity. Otherwise, it will continue with whatever velocity it has. So we call this law, Newton's first law, is also referred to as law of inertia. Now, you know what is inertia in general means? Inertia, like someone resists a change, that inertia. Okay, if you are sleeping, you want to keep sleeping, so you can say inertia. Or if you are sitting down, you want to sit down, laziness, inertia. Resistance to change is inertia. So here, we are saying if a body has a certain velocity, that's a state of motion, it wants to keep that. It doesn't want to change its velocity. So it's an inertia. So Newton's first law is also referred to as the law of inertia. When an object is either still, meaning at rest, or in a state of uniform motion, meaning constant velocity, then it wants to continue like that because there are no net force acting on it. So it will, like, say, for example, an ice surface, okay? And we have an object, the ice hockey puck, let's say, say it has some velocity. It will go forever, right? Provided there's no air resistance and it's perfectly smooth, the ice has no friction. The force is zero. It has a net force zero because, see, vertically we have forces, of course, but the vertical forces are balanced. So that's why it is not moving up and down. So there are no horizontal forces. So the net force is zero. Suppose it has certain velocity, it will go forever. As long as there is no friction, it is keep that velocity forever. For example, in the space, far away from any other object, there are no forces. And if there is one single object, that object has a constant velocity. It can be zero or some other value. So this is the law of inertia. So force is needed to change the velocity. If there is no force or net force is zero, the velocity will not change. So we can say the net force zero in this way. And if the net force is zero, the body is in equilibrium, or you can put it the other way. If the body is in equilibrium, either moving with zero velocity or some other velocity, not moving. Zero velocity means it's in the same place. You can apply the equilibrium condition in any direction. So we usually take two directions perpendicular to each other. So we will have two independent equations. Then we can solve problem to find some unknown forces. Okay, so that is Newton's first law. Actually, we kind of did this in chapter 3, the equilibrium condition, right? If the net force is 0, the body is in equilibrium. So the net acceleration is 0. All right. An object at rest or in motion with constant velocity remain in its state of motion unless acted upon by a non-zero net force. This is the statement of what? Newton's first law. Okay, this is a proper technical way of expressing it properly. An object at rest or in motion with constant velocity remains in the same state of motion unless acted upon by a non-zero net force. So let's test how much we understood this by a concept question. You are sitting next to a driver in a car traveling down a road. So you're in the car. Down mean not down. Okay, that's a phrase. From that's all. You are going in a car with a constant velocity. Suddenly, the driver applies the brake. What happens to you? You are pushed forward, right? And now, can you explain it in terms of the law of inertia? Yeah. Yeah, but you apply the brake. You apply the force. You are, yeah, okay, yeah.
Because I am moving in
certain constant velocity.
Speed change. For that reason.
No, you didn't change. You continue.
Yes.
Yeah.
But for the car.
For the car, there was a force. Yeah.
The force action me is 0, so the velocity will
remain constant. But what for the car? What happened to the car when you put the brake? Why a car stopped and you didn't stop? Yeah. Yeah, but car didn't resist the change. The brake is on the car, not on you. Okay. You know what happened when you put the brake? The pad pressed the tire, right? I mean, so yeah. Okay. Yeah, okay. We'll come to that. Yeah. Inertia. Yeah. Oh, that is because of inertia is just as if you understood everything, right? I think you understood. Yeah. So short answer is inertia, but you didn't explain in detail, right? So let's explain it in detail. So you and the car having a constant velocity. You and the car having a constant velocity. Because your net force on you and the car is 0, that's why you have a constant velocity and you are moving. When you apply the brake, what happened? You apply a force on the car. Everything that is connected to the car, the force will be felt, right? So the wheel is where the brake is applied and the wheel is connected to the car. So when the wheel stops, everything that is connected to the wheel will stop. Are you connected to the wheel directly? No. You are sitting on the car seat, but you are not glued to the car seat. So still the net force on you is 0. I'll come to the friction in a minute, okay? The net force on you is 0 when the brake is applied. Let's assume there is no friction between the seat and you, okay? So when the brake is applied, the net force is applied to the car, not to you. So you have no issue. You have to obey the Newton's first law. You will continue going with the same velocity, but the car, because there is a non-zero net force is now there, it will stop. And you will go, then you hit the steering wheel, then there is a force on you, non-zero net force. You will stop. Okay, now you will ask, what about the friction between you? The friction is not big enough to stop you. It is there, it will come into play, but okay, it will reduce your speed, okay, but not to stop at once. But the brake will stop the car, at least not at once, but the friction force is not as great as the brake force. So that's the reason why the car stops and you still move forward. So let's read this. I mean, whatever I said now, but let me read it anyway. It is nicely written. When the driver hit the brakes, the brake, the non-zero net force, is applied on the car, not on the passengers inside. So the passengers continue to move unaffected until the seat belt or the airbag or whatever else in front of him, the steering wheel, stop her from moving further. One should also note the friction between the passenger and the seat also come into play, but that friction is not great enough to keep him stuck to the seat. It's not really glued like the rest of the thing to the wheel. Right, so we got another concept question on this. For each of the 6 objects whose free body diagrams are shown in the next page, the arrows indicate forces of equal magnitude that act in the directions shown. Which of the 6 objects are not in mechanical equilibrium? It's an easy question, right? Equilibrium means the net force has to be 0. So if you look at this one, they are all equal magnitude. If I call this force 1, force 2, force 3, force 4, can I say 1 plus 2 plus 3 plus 4? The vector addition is 0? Yeah, because 1 and 3 will cancel, and 2 and 4 will cancel. So whole thing is 0. And it's the same here, net force is 0, because they're all equal magnitude, but in different directions. But these two, there is no equilibrium. So that is the answer. One more, 6 also. 3, 4, 6 are not in equilibrium. Okay, another concept question. The 3 forces are acting on a human leg. The weight, the normal force from the floor, and the force F on the hip bone exerts on the head of the femur. Is the leg in equilibrium? So this is the picture. So we are taking the leg as one object and the forces, external forces acting on them. We can say the gravity force, the weight of the part of the leg, let me call it W. Say maybe this is the center of the thing. And then normal force from the floor on at the foot, let me call it N. And then the rest of the body above your hip has a weight, right? That will be pressing. There's a contact force here. So that let us call F. Now, are the forces, net force is 0? It has to be because it is in equilibrium, right? We are not moving, standing. So the net force has to be 0. So this means if I bring all the forces here, so this is N up and F down, and we got the weight, right? Instead of drawing it here, I will draw it here for a simple reason. I just want to see that this length must be equal to this. So that's how they should put it. Yeah. Friction comes into play. There is a parallel force between the contact here. The friction must be here, right? Between the foot and the floor. If it is moving horizontally, then there will be friction. Yeah, no, you're already standing, you're not moving. The question is somebody is standing. When somebody is standing, these are the forces acting on the leg. He's not trying to move anywhere. Yeah. Yeah, if you stand on ice, well, if you stand without moving, you will manage to stand. Only if you try to move, you'll be in problem. Okay. Not necessary. If there is a slope, only you will move. You can stand, and if you keep your balance, if you don't tilt to the side or something, then you will start moving. Yeah, but what's the relevance to the question here? Yeah. Ice, yeah. Flow. No. Actually, friction make you also enable you to move, you know, in one sense. Yeah, I understand what you're saying. Okay, I can understand what you're saying. But anyway, here there is no friction. What I'm trying to tell you is because this is not moving, you will have friction. The friction is there, but it is not acting on it. I'm not telling there is no friction. The friction come into play only there is a slipping between the contacting surface, a motion between the contacting surface. If there is absolutely no motion, or you're not someone trying to push you, then there is no friction. Okay, so, okay, let's stop there. Right. Yeah.
In this case, we have friction, but it's not involved in that.
It is not involved. The friction is, there is friction between this, okay, but it is not coming in. It will only come into action the moment the guy starts to slip on the floor, any contact, right? Of course, there is friction here inside. Those are internal forces. Between the bones joined, there will be friction. Here, okay, there will be friction, but it's again only if if you try to, bend or do like that, there will be friction. Yeah, okay, yeah. Why is there? Yeah, well, it's an approximation. Okay, so we are assuming. Okay, this is, of course, this is perpendicular. The normal force must be perpendicular to the surface, so it is vertical. Gravitational force is vertical. So the only question you can ask is for this guy. So we are assuming, so the bone here is touching exactly, so it will be from your upper body, right? The weight of your body will be that's also actually a normal force. This F is actually a normal force between what is this bone called? Hip bone, and this is the femur bone, right? So, right. Well, I don't know, we're unnecessarily making it into a big thing, but I just want to show you. Excuse me, please. Okay, for example, how this is important for a doctor, for example. You can calculate this F roughly. That's an important factor because, the hip bone is supporting that much of weight. Say, for example, can you give me a rough value for N? N, why not? It's half of your body, right? You are touching the floor only in two places, left leg and the right leg. So your whole body weight is divided into two. So suppose your weight is 80 kilograms. So N will be, and I don't want to convert it into Newton. Okay, I just want to, take the weight as kilogram, no problem. You have to multiply by G, but let's keep it in kilogram. So N is 40 kilogram. So the N is 40 kilogram. What do you think the weight of the one leg alone? 10% of the weight? 10%. Let's take 10% easy, okay? So weight of the leg is 10% of 80 kilogram. 10% of 80 kilogram, 8 kilogram. Okay, right. So if you apply the equilibrium condition, you can see F plus W is equal to N. So F is equal to N minus W. N is 40, W is 8. So 32 kilogram. The leg has to support at the hip junction, hip joint, 32 kilogram. So maybe some valuable data as a doctor, right? So we apply physics now to medicine. Yeah.
The weight of the leg, not the whole body.
Oh, yeah. I'm telling, so 10% of your whole body, say 80 kilogram. Let's say you are 80 kilogram. 10% of 80 kilogram is 8 kilograms. So I said the leg only, one leg, not both legs. Okay, we are looking at one leg.
The normal force will come
Oh yeah. Because you are standing. Because if you take the person, what is the free body diagram for the person? The weight of the person and the normal force on his leg, 2n up. So 2n is equal to weight. So n is equal to weight divided by 2, because the normal force is in the 2 legs, right? But if you stand on 1 leg, then the normal force will be the whole total weight. So that's why you feel more pressure on your leg. Okay. Numerical example. An object of mass 1 kilogram is attached to a string of length 2 centimeters. The object is held. I should take attendance, so let me pause. Okay, so an object of mass 1 kilogram is attached to the string of 2 centimeters. The object is held stationary by external force. Oh, let's go to the picture. Okay, this is the question. We have an object, there's a string attached and another force, so it is in equilibrium. So the length of the string is given, I don't know why. So the tension, let me call is T. So the tension force will be like this on the ball. And do we have any other force? Gravitational force. Yeah, it is. You know, this force is in both directions, right? We need to get both X and Y. Let's say, okay, we are not going to completely solve it, you know, because I want to, before people leave, I want to, so let me go a little faster. So anyway, I mean, we'll go gradually, okay? We'll not go to the solution at once. I know you can do it, but let's go slowly. I want to stress this free body diagram. So what is here to do first to show all the forces. So this object is interacting with this string, and this another string, someone is holding it, okay, this. And the earth, you cannot escape. It has got only 3 forces. It's not contacting anything. There are no surface forces. It has got 3 forces. Yeah, normal force and the parallel force is between contact, right? When it is touching something, is it touching anything? No. So there's no normal force, okay? So you just look at what it is interacting with. These are the only 3 forces. What is the next step? Is to choose the X direction and the Y direction. It's a two-dimensional. The forces are, if you look at the tension, for example, you know, one is in the x-axis, other one is in the y-axis, in a plane. It's a 2-dimensional problem. So we have to consider the 2 direction. At least you should be happy we don't have to consider the 3rd direction, because the space is 3-dimension actually. So at least we are happy, okay, it is only 2-dimension. Now I can say the question is to find these 2 guys. These are not given, only the W is given, the weight is given. Can we find these 2? Yes, because we got 2 independent equations. One along the x-axis, net force in the x equal to 0, and the net force in the y equal to 0. You may need both. Maybe sometime you need only one of them, depending on what the question is. Suppose the question is to find the tension only, you need only this equation. Because in this equation, no, you need the y equation. Because we don't know this, right? So, but we know the W. So if the question is find T, we only need this sum of forces in the y direction is equal to 0, right? Because this guy will not bother us in the equation, so we can find it. And suppose you want to find only the this guy, then I need the equation in the x direction, because he will not come and bother us. No. Okay. If you need to find the F external, we need both equations. First, y solve first, then find tension. Then after that, you can come to this and find the external force as well. So you have to go in 2 steps, okay? Right. So here my point is, what the best thing to do is to resolve this get rid of this t and call it ty and tx. So all the forces are either in the x direction or the y direction. Okay, so forget about that. Okay, no. I mean, what I mean is here, see, this tension force, right? Not in the x-axis, not in the y-axis. So then we just if we know this angle theta, right? So I can say this is t sine theta is the x component, and the t cosine theta is the y component. So I can, instead of this tension, I can replace it with two forces. Why do I do that? Then it will make it easy for us to apply into the equation. That's the only reason. Because when you write sigma fx equal to 0, I can forget about this guy and this guy, because they will have no contribution. So it will be simply t cosine theta minus f external equal to 0. Right? Good. All right. I think I'll stop there. Thank you. Yeah. Yeah, if this is the angle theta, because theta is with the x-axis, y component will be sine theta, x component will be cosine theta. Oh, this is, I'm sorry. If this is theta, this is not theta out, so I got it all wrong. All right, okay. Thank you. I wrote there theta, but actually this is the theta. That means this is not theta, this is the theta. So the, all right, it is in the slide, so please follow. Yeah, of course. Yeah.
I didn't, I went to the bathroom, I didn't see this.
Oh, yeah, all right. This is acted upon by, let me stop this, okay, so. Right.